Hello, let's now have a look at DC motor drives, where we apply the DC motor to different traction applications. First, feeding from AC supply, and as I mentioned before, we will use some kind of a diode or thyristor rectifier. Historically, we had diode rectifiers with transformers with tap changers, so we could vary the input voltage. Later on, half-controlled thyristor bridge was the common choice for this kind of application, for this kind of drive and application. That is, we have diodes in one of the phase legs, and we have thyristors in the other phase leg, as described in Chapter 3 of the textbook. So this is connected to a transformer on the second, connected to the line. We have the pantograph. We have the DC motor. This constitutes the complete drive of a DC traction train. This shows, as we described in Chapter 3, there is an issue with the line conditions, with harmonics and with the capacitive, with the inductive loading of this kind of train on the supply. This drive inherently consumes reactive power. So let's look at different operating conditions. This first is with alpha equal to 90 degrees. That is, we get more or less a pure inductive operation with hardly any kind of active power. As you can see here, we have the voltage and we have the current with roughly not really, but almost a 90 degree phase shift. This is the freewheeling current, the current that goes through the diodes and the motor, and this is the motor current, which is then continuous. This is the output voltage on the motor with a small DC component UM. So in this case, UM times IM produces the little active power the train produces. That can be transferred into some kind of tractive force. To the right, we have a fully controlled or non-controlled bridge. That is, alpha equal to 0. In this case, the bridge works as a diode rectifier. And as you can see, voltage and current are almost in phase. We have a smooth motor current. We have no freewheeling current because at alpha equal to 0, when we have no control of the thyristor bridge, there is no freewheeling mode. And then, of course, the DC voltage is this 2 pulse, half pulses rectified voltage. So UM times this IM is the active power that is transferred into tractive force. Looking at this picture, we realize that there is a problem with the consumption of reactive power with the inductive operation. So there are different solutions to overcome this relatively big consumption of reactive power. The most common one used is to use series connected thyristor bridges, 2 or 3 bridges in series. The idea is to operate them one at a time. The first bridges, all bridges are first controlled to alpha equal to 180 degrees. Then the first bridge is controlled from 180 up to 0. And then the second one after that, and finally the third one, if there is a third one. That is, they are not controlled with the same alpha, both bridges, or all 3 bridges. They are controlled with different alphas. In that way, we will get a much better waveform and less consumption of reactive power in between the 0 and the maximum point, as I will show you in next coming pictures, or the next coming figures. This is an example of what it looks like with 3 rectifiers in series connected on the DC side. Typically, this is today replaced by 2. It's more common to have 2, but you need at least 2. You can never have fewer than 2 because that would create too much reactive power. This is an example for an old locomotive built in the 60s, late 60s. At that time, the ratings of the thyristors was so low, so you required 3 bridges to get full voltage. This shows the power factor for some of these different connections. Number 1 is what it should be if all the bridges were controlled with the same alpha. This is typically a half bridge. And you can see it's very poor power factor, lambda, at low speeds. and here at base speed, 100% of rated speed or base speed, we get up to full voltage, alpha equal to 0, and we get a constant value approximately equal to 0.9 of the power factor. The second one is a bridge with a turn-off capability, that we are able to control the current to be in phase with the voltage. That only generates harmonics or distortion power, so there is no phase shift and there's no consumption of reactive power due to the phase shift. It's only due to the distortion of the line current. Then we get a much better power factor, substantially increase the value of the power factor. This is a pretty complicated bridge. There are very few examples of trains with this kind of bridge, if any. Prototypes, yes, but this was at this time a very complicated solution to get this. And most likely AC drives were introduced before this became a very simple solution to build. The third one is the one which actually is used, and this is the series connected half control bridges. As you can see, if you do this kind of control, and with this kind of series connected bridges, you will get a peak in power factor at half the base speed. That is when the first bridge is fully controlled up to alpha equal to 0. And then it goes down again when we start to change the triggering angle alpha of the second bridge. And that one is then going down and up again until we reach base speed when we go to the same conditions as for the half control bridge, because then of course at alpha equals 0, it doesn't matter whether we have two bridges or one bridge, they provide the same result. This shows some little bit a glimpse of the problems we create with the thyristor bridge, with a half control thyristor bridge. This shows the line current, which is not at all sinusoidal. This is at a low speed, and this is at a higher speed. As you can see, it's not only the line current that is distorted, also the line voltage will be distorted. Imagine these are basically sinusoidal curves, sinusoidal waveforms, which due to the commutations of the thyristor bridge, due to the operation of the thyristor bridge, generate a very distorted line voltage, which can be seen from measurements. And as you can see to the left, when you have a very poor power factor and a very high alpha, basically, to get a low speed, we actually have problems with multiple zero crossings. So this is really a non-wanted waveform. It's a little bit better when you operate at 90 kilometers per hour, because then you have alpha equal to 0 and basically you have full voltage out and a minimization of the reactive power. Finally, this shows a circuit diagram of a typical DC motor thyristor locomotive. This is a train fed from a 15 kV 16 Hertz supply, where you have DC traction motors. Here you have the armature windings of the 4 motors, and in this here you have the field winding. This is a control of the field winding. Then you have the 2 thyristor bridges, series connected, and to the left you have the transformer, and this transformer is a one with a low leakage inductance in comparison to the one we have at AC traction drives, where you have a high leakage inductance. This is due to the fact that the commutation, the turn on and turn off of the thyristors in this bridge is going through, via the secondary windings of the transformer, and to do that quick, a low leakage inductance is required. As you can see, there are quite some windings in the transformer. These are the windings for the field windings, and they have the windings for the traction motors, and of course then you have windings for auxiliary power and for train heat and so on. That was the normal operation. If you want to improve the train a little bit, you can add a capacitive filter so that you compensate the consumption of reactive power by introducing a capacitor. This is used in 50 Hertz systems, for instance. To my knowledge, not used in 16 Hertz systems. It might be that the filter become too bulky. This would improve the power capacity of the train somewhat. And of course, that is required when we have this drive, which inherently has rather poor operating conditions regarding harmonics and reactive power. So that was AC supply. Let's have a little bit of a look at DC supply. And this is, of course, typically what you have for subways, trams, but also for some main lines. And in this case, as we've seen previously in Chapter 3, you have the DC motor. You have, in this case, a step-down chopper consisting of a switch. It could be a GTO or an IGBT. And you have a diode. And on the line side, you have a low-pass filter, an LC filter, which is a low-pass filter. Because from the grid or from the power supply, you want to draw mostly DC current, of course. You want to filter out any high-frequency components of the current. And to the left here we have the field winding that controls the flux of the machine. And as we remember from Chapter 3, this is the pulse width modulation. The power supply is E, and by controlling the width of the pulses, we can control the average value of M, that is the DC value of UM, that is the voltage across the DC motor that determines the speed of the DC motor. So principally, the DC motor is controlled by controlling the voltage amplitude, and the AC motor is controlled by controlling the frequency of the voltage supplied or applied to the motor. In this case, you can see 4 distinct operational modes. The motor operation first, and when the switch is on, the power is drawn from the power supply through the inductance of the filter, through this switch, and this is a case when you have a mechanical switch for motor and generator operation, through the motor and to the switch, back to the switch, down to the wheels, to ground. And when you turn that one off, the current will, due to this inductance, start to freewheel in this circuit. The corresponding operating conditions at generator operation is that this switch is open, and you have the switch on mode when the current goes from the inductance through the switch and back this way. And when the switch is turned off, it means that the power is pushed up to the DC supply through the diode, and the current goes this way, up through the diode and to the power supply of the DC power supply. When you have this kind of DC motor drive, you can add a braking resistor. That is a separate resistor connected in series with the motor. And this is something you can do simply. You can when you brake, if you have 0 voltage here, you have 750 volts here. If the current is going backwards, you will get a voltage drop across this resistance RS, which means that this potential here will be below 0. That, of course, will generate a higher voltage across the motor. If it's 750 volts here, and if it's a negative voltage here, the voltage across the motor will be higher than 750 volts. And, of course, it will provide us with a higher braking force. So this kind of drive can simply be designed to have a braking power or braking force diagram, which is different from the tractive force diagram. This is for tractive power, and this can be for braking. That is, we can have a higher power when we brake. This can somewhat be done also with AC traction drives, but then you have to operate with a varying DC power, DC link voltage, and that you cannot do with DC power supply, but you can do with AC power supply, because the DC power supply, the DC link normally has the voltage of the power supply, which makes it possible to increase it, so to say. This shows the main circuit of a tram equipped with DC motors and choppers, or these DC-DC converters. You can recognize the motors here, the field windings. You have the inductances here. You have the step up, the converters, the step down converters. We have the thyristors and the diodes here. You have the braking resistances here, RS and RS separated into two parts. You can have two steps. You can have one braking resistor. You can have two braking resistors, depending on if you want more braking or less braking. And you can, of course, if you want to disconnect them completely or short circuit them. And then you have the contactors, mechanical contactors that determine whether you had braking or motoring. So this pretty much shows what we have in the previous pictures put into one train. To the left, you can also see that there is some kind of over voltage protection. That is a controlled resistance that can consume power if you need to lower the voltage, and then you have the filter inductance LF, and you have the filter capacitance C here, and of course you have breakers. You can also ask, why do you need the contactors? You could have a full bridge instead to operate in motoring and braking. Well, at the time when these trains were designed, still semiconductors was a costly and complicated device. So actually it was you wanted to have as few as possible. So in this case it was simpler and more secure to use some kind of a mechanical contactor instead of more semiconductors. Today it would probably be designed in a different way.